So, who has questions? We'll be starting chapter 19 next week. And then after next week, we have an exam covering chapters 18 and 19. Not this Monday, but next. So, we got some extra time in the schedule. Is a good time to do some review, ask questions, any of the material we've covered that aren't up to speed on yet. Thank you. Who has any? Everybody's up to speed on all of this? Really? Cool. So, I got to tell you, I've been like half a step off of balance for like the last several days. Couldn't figure out why. It's like, what's wrong? Why do I keep? But I think I figured out what's happened. I fell behind in my work, and I've been a little bit behind. I've still got a few papers left to grade that I haven't graded yet. A couple of them from this class, and at least one from one of my other classes. I don't know why it is, but it is generally true that when I fall behind, I get off balance. And it's like I have more things going through my head than I can keep tabs on, and I end up getting off kilter. So, that's just me belly aching that in bed. That won't be on the test, so don't worry about it. But what might be on the test is any of the stuff we've covered. So, if y'all don't have any other questions, then I want to go back and revisit that whole drift velocity thing. Because I know I said that I didn't really care for it being in the book, being in the course. I'm not sure I still agree with that. I'm not sure I still think that. I think I can tell you that it's not something that'll ever come up again. You're never gonna, doesn't matter whether you're working on high line, power lines, or AC refrigeration, or if you're a technician fixing the electronics in a car, or you're working at a national laboratory or NASA. You're never going to have to worry about the drift velocity of an electron in a wire or a conductor. But it's just surprising. It really is shocking at how slow those electrons actually move, in terms of their net drift, how fast they drift along that wire. And to think that you could literally walk faster than the electrical current flowing through even a high power line is a little bit startling, and I think understanding it, even though it's not something that you're ever going to use again, I think understanding it will benefit you from the fact that you do understand something with a little more intuition than you otherwise would have. So, let's go back and look at it some more. Now, we've got a drift velocity, V sub D, that we want to know. Okay, first of all, think back to the mechanism of what's happening as these electrons are moving, or migrating through a conductor. You have a conductor that's basically a lattice of copper. We'll use copper as the example, of copper atoms in a lattice structure. Okay, and those atoms don't move, they're fixed. But every one of those atoms has a free electron on its valence shell that's free to move from one atom to the next. So when that electron takes off, when an E field or a potential starts pushing that electron, it's going to take off in some direction until it has a collision with one of those other atoms, and then it's going to bounce off in some direction, any direction, no telling which. Point is, we like to think of electron flow in a wire the way we think of water flow in a hose. Like either maybe it's turbulent flow or maybe it's laminar flow, and that might be a good analogy to think of. But we tend to think of it as laminar flow, where the water is just shooting right through. But if you ever study the Reynolds number and turbulent flow, how many of you ever worked in a refinery or a plant where you've dealt with heat exchangers? You've all got radiators in your car. If that water ever starts flowing through that radiator in laminar flow, that radiator is not going to keep your engine cool anymore, because the heat that builds up in the water won't be able to migrate out through the copper tubing into the atmosphere as easily. That water flow through that radiator needs to be turbulent, not laminar. Well, you can kind of think of electrons moving through a wire as turbulent flow, because they're not moving in a straight line. They're bouncing off of all of these atoms in all manner of random directions. We can observe it macroscopically in what's called Brownian motion. You can look at microscopic particulates floating around on the surface of water, floating around in water. And even though everything is just sitting still, they still move around randomly. It's called Brownian motion. And it's the same kind of effect. It's collisions, bouncing off of molecules and atoms. So the point is that as this current is flowing, so many coulombs per second is flowing past every point in that wire. Those electrons have to have some net drift velocity that they're moving, speed they're moving along the wire at. And it's shockingly slow. Okay? So let's go back and revisit that. We know that there is a certain amount of current in the wire, and that in a time delta t, the electrons will travel a distance L along the wire that is equal to the drift velocity of those electrons times delta t. Okay, so in delta t, the distance that those electrons travel is equal to their drift velocity times that delta t. Now, that whatever the wire, it has some cross-sectional area, A. And so, in that same amount of time, delta t, those electrons are going to travel through a volume of that copper wire that's equal to the length that they travel times that area. There's a volume of that copper wire that's equal to the length times that area. draw that as that chunk of the wire. So how many the point is that the electrons in that volume, A times L, are going to cross out of here. They're going to all cross this plane in this length of time, delta t. Okay. Does everybody see that? At a moment in time, t0, there is a fixed number of electrons in that volume of wire. And they're moving at a velocity of delta t, of drift velocity. So in a time, delta t times that drift velocity is this length, that whole volume of electrons is going to move from here to there. Okay, so that whatever volume of electrons started off in this volume at t0, at delta t later, that whole volume of electrons will now have moved over to here. So that's how many electrons passed through this plane of the wire, or past that point in delta t. Now, if there are n free electrons in this chunk of wire, and each of them has a charge of E or Q, then the total charge that moves, there are n electrons in that volume, and each one of them has a charge Q, or the book uses E, but we've been using Q all semester, so I'm going to stick with Q. Then the total charge that moves out of this volume across this plane in delta t is equal to, the total charge is equal to N times Q. Now, that is how many electrons move across that end plane of the wire in delta t. So, the total charge that passes this plane is N times Q. And why do they? Okay, then they talk about the total. Yeah, see, this is, okay, I told you I'm missing a beat every once in a while. Yes, see, this N is the number of electrons per unit volume. That's the difference. Where N per unit volume, N is the number of electrons per cubic meter per unit volume. So the total number of electrons, N, is equal to the number of electrons per unit volume times the volume, which is this here. Right? So if we have N electrons per unit volume times Q charge per electron times this volume then that is what equals the total charge that passes through this plane, okay, in that unit of time, delta t. So when we divide that total charge by delta t, we cancel out here, we end up with the total charge per delta t per unit time is equal to the number of electrons per unit volume times q times the drift velocity times the cross-sectional area of the conductor. Okay. Well, the amount of charge per delta t, the coulombs per second, is simply the current, I. So now, that means we have an equation here that relates the current flowing through a wire to N times Q times area times drift velocity. It relates the drift velocity of those electrons to the current flowing in the wire. It depends on this number here, the number of electrons per unit volume. That's always a bug. That's always a bugaboo that's going to get you. You got to keep it straight. Question is, and this is where you got to start getting into a little bit of chemistry. How many electrons per unit volume do you find in a chunk of wire? Okay? You understand the question? You've got a unit volume of wire, of copper. How many free electrons are in that unit volume of wire? If we know that, then all we got to do, we know the charge, we know Q is what? 1.6022 times 10 to the minus 19 coulombs per electron. Okay. We can look up the area, cross-sectional area, if we know the diameter of the wire, if we know the gauge of the wire, we can look it up on a table. You can measure the diameter of the wire, the cross-sectional area. And we can measure the current, or if we know the resistance and the voltage, we can calculate the current. That number of electrons per unit volume. That's the bugaboo. Where do you get that number? Well, if you look in the back of the book, copper has an atomic mass of 62.5, 63.5. And they call it 63.5 U, or units. Atomic mass units. Okay, what is an atomic mass unit? No. Get the atomic mass unit is, frankly, they just kind of arbitrarily decided it's 1/12 the mass of a carbon-12 atom. I don't know why they chose it. They did. Carbon is the most common organic element. I don't know. Doesn't matter why they chose it. They chose it. It actually works out to 1.6605 Doesn't say right here. Hold on a second. I don't want to mess this up. And like I said, I've been missing too many beats this week to take a chance. Let's see. Yeah, I was right for once. 1.6605 times 10 to the minus 27 kilograms. Very nearly. It's almost the mass of a proton. The mass of a proton is 1.67 times 10 to the minus 7. So, yeah. For the mass of a proton, it's right here in the cover of the book. Yep. Or 1.00728 U. Okay. Mass units. So, that is, so a copper atom, one copper atom, can't even write this week, one copper atom weighs 63.5 times 1.6605 times 10 to the minus 27 kilograms. So, if we look up the density of copper, we're going to find that it's 8.9 times 10 to the 3 kilograms per cubic meter, according to this. $8.9 times 10 to the 3 kilograms per cubic meter. That is the density of copper. So how many atoms of copper are in 1 cubic meter of copper? Got 63.5 times 1.6605 times 10 to the minus 27 kilograms per atom. Or 1.0544 times 10 to the minus 25 kilograms per atom of copper. Everybody see how we got that? Cyrus? Okay. Well, if there are 8,900 kilograms of copper per cubic meter, and there are that many kilograms in each atom, how many atoms are there in 1 cubic meter? Well, if we divide 8,900 by 1.055, 0544, times 10 to the minus 25 kilograms per atom. Look at our units. We're doing kilograms per cubic meter divided by kilograms per atom, which is the same as multiplying kilograms per cubic meter by atoms per kilogram. We end up with 8.44 times 10 to the 28 atoms per kilogram. Of copper. Yeah, not you. Thank you. Not kilograms. Atoms per cubic meter. Thank you. Y'all all really need to keep me on my toes today. So, what were we looking for? This is the number of atoms per cubic meter. This number here, the density of atoms per cubic meter. Okay, why am I saying? Actually, we said this number was the number of free electrons per cubic meter, right? Well, in order to do this calculation, we're assuming that each atom in each cubic meter provides one free electron. So the number of free electrons is equal to the number of atoms in each cubic meter of copper. And that, in the book, they used some molar calculations to do all this. Let's find out how close we get to their result. What cross-sectional area were they using in this example? Yeah. You're not? Ten to the minus 25. Well, let's try this again. 8,900 divided by 1.0544 times 10 to the negative 25. Yeah, I get 844 times 10 to the 28. And so, they're saying the cross-sectional area is, they're saying the radius of their wire is 1.6 times 10 to the minus 3. meters. So the area is pi times 1.6 times 10 to the minus 3 meters squared, which would be 8.04 times 10 to the minus 6. Let me make sure I counted that right. Times 10 to the minus 6 square meters for their area. And in this example they're using, what is their current? 5.0 amps. So, clear up some space to do the calculations. And we've got I equals N times Q times the drift velocity times the area. And we want to solve for drift velocity. So we're just going to divide current by N Q and A. And that will give us the drift velocity of those electrons flowing in that wire. Now if the current is 5.0 amps, we calculated that there are 8.44 times 10 to the 28 atoms per cubic meter. We know there's 1.6022 times 10 to the minus 19 coulombs per electron. And the cross-sectional area is 8.04 times 10 to the minus 6. That gives us a drift velocity of 1, 2, 3, 4, 5. You got how much? Yep, that's what I get. Or 4.6 times 10 to the minus 5 meters per second. No. That would be 0.05 millimeters, 5 millimeters per second. Or times 60 seconds per minute. Yeah? No, 3 millimeters. And if we multiply that times 60 minutes per hour, that's 0.17 meters per hour. That is, I don't know that we can walk that slowly. I mean, seriously. This is a 5 amp current in an 8.04 times 10 in a well, it's 1.6 millimeters radius, so that's a 3 millimeter diameter wire. If you've got a 3 millimeter wire running, or 3.2 millimeter wire actually, running 5 amps through it, you cannot walk as slowly as the electrons are drifting along that copper wire. The voltage, that's what propagates at the speed of light. The potential, the E field. Now that speed of light right down that wire. But the electrons really are not that fast. I mean, they are shockingly slow, no pun intended. They're surprisingly slow. Kind of like the old joke about computers. Computer's a blithering idiot, but it can blither a bajillion times a second. So, the average speed of a given electron, not very much, but there's so many of them that it still hurts. They're still delivering a whole lot of energy, even though each one's only delivering a little tiny bit. And if we look at their solution of the problem, yep, we see right here they got 8.4 times 10 to the 28 per cubic meter of the number of atoms, or number of electrons. So, who has any other questions? No, it's the current. You get shocked. You zap yourself with when you touch the doorknob. You see a spark that long. That's tens of thousands of volts that you're getting hit with. Because the breakdown voltage of air is 3 million volts per meter. So that just a little spark that long, you're talking about tens of thousands of volts. But it doesn't really hurt you. I mean, it hurts, but it doesn't harm you. And that's because there's so few electrons involved that it's not really transferring much energy at all. It's very much like the transfer of heat. You know, how hot does something have to be before it burns you? You've ever dealt with fluorescent light bulbs? Up there and grab that bulb and handle it and turn it and undo it and not worry about burning yourself, right? But that light bulb, plasma inside that light bulb, and therefore that's a, I don't know, 10, 15,000 degree plasma. That's how hot the plasma is. That's the temperature of the plasma. But that's not a very accurate reflection of how much energy, how much heat it would actually put into it, because it's a very small amount of heat. Very hot, but a very small amount, so you could handle it, it wouldn't hurt you. It's like the oven, when you take something out of the oven, you're going to grab some pot holders to grab the dish or the pot or the pan because it's hot. But you don't have to put your arms inside thermal blankets to reach into the oven, even though the oven's 400 or 500 degrees hot, because you're going to be in that very hot temperature, but not going to have enough time for enough energy to be transferred into you to hurt. Same thing with voltage. You can have lots of voltage. It'll knock you for a loop. It'll sting. It'll hurt. But it's the actual electrons that are being transferred. It's the transfer of energy in the form of charge that's actually delivering the energy, doing the work, producing the harm, not the voltage. And that's intuitively what most people think, but it's just not true. It's about how many electrons are passing a given point per second. And there are literally bajillions and bajillions of electrons per unit volume inside that copper. And so they don't need to move very fast in order for a coulomb's worth of them to pass a point in the wire every second. They just don't. That might be a more interesting problem to look at. If the electrons, we know now how many electrons there are per unit volume of copper. If the electrons were moving at, I don't know, 5 miles an hour, which is a good walking speed, how much current would that be? We'd find out that would be billions of amps. It'd just be bajillions of amps of current. This is a thing that I hope y'all take away from this class, is that when we start dealing with very, very large numbers, that the impact of those very large numbers can be dramatic. And this is one case where it's surprisingly so. For air, yeah. Right here, page 512. That's exactly one of the example problems they gave. And they're saying that lightning strike is about 50 million volts. You can measure. In fact, if you recall, we did that in the lab we did on capacitance, where we estimated the length of the arc from the Van de Graaff sphere to the discharge ball. We got the length of that arc, and then used that length divided by the breakdown voltage of times the breakdown voltage of the air of 3 million volts per meter times that many meters gave us how many, like a couple 100,000 volts or something. Just for a little bitty short arc, a couple few inches long. There's a movie called Running Scared. And it has Billy Crystal and Jeffrey, who's that dancer? Huh? No, not Michael Jackson. No, I can't remember his name now. He's actually a very good, famous dancer before he became an actor. Yeah, no, that was a whole different kind of dance. Anyway, there was the movie was called Running Scared, and they were detectives chasing the bad guy, drug dealer, or whatever. At one point, they were chasing him in their car, and they jumped up on the subway tracks, the L, then they call it in Chicago, the elevated railway. And the Gregory Hines, that's his name. Billy Crystal told him to watch out for the third rail, because the third rail got like 600 volts. At which point Gregory Hines said, yeah, but it ain't the volts that kills you, it's the current. And so Billy Crystal said, okay, well, how much current does it have in it? He said, enough to push a train. Stay off of the third rail. And that's that, but that really does. That kind of puts it in perspective. We talk about all these big numbers with the exponential notation, and that's all well and good, and we should understand them. But at the end of the day, you need a perspective, and that's a good perspective. There's enough current in that rail to push a train. That'll hurt. It's like that warning sign that said, it's not even that much. It's like a couple hundred milliamps. Yeah. No, well, 0.5 will do it. Yeah, I thought that was like. I don't really, I'm not really an expert on killing people with electricity, but my understanding is it's more like a couple hundred milliamps. I'd have to take your word for it. I can tell you that 120 volt electricity is more dangerous than 240 and more dangerous than 480 or 600. Because when you get up to 240 and above, if you do touch it, if you do get hit by it, it's going to throw you away. It's going to throw you down. That 120 will grab you and hold on. And he didn't. Yep. Angry, yes. You were so angry. Yes. I don't blame you. I would have been angry too. Yeah. We had in fact, I still have a few of mine from when I worked at the Super Collider. That everybody had their own lockout, tagout devices, locks and tags. So if you were going to work on something, you went to the breaker or the switch to turn it off, and then you put on the lockout, tagout. Or if somebody else already had it locked and tagged out, and you were going to be working on it, then you just add your lock to the device with your tag on it, and that way nobody else could go back and turn it on until you did. Yeah. Yep. That's the little lab. Yep. There were laminated tags. Yep. The yeah. Well, the tag came with, we also had our own locks. So no one else could have the key to your lock. So they couldn't take yours off. Yep. And it had it was like the little things that would do this, but then it had there was this pivot point, and then there was like an array of holes. So exactly, and every person could come along, and anyone could come along and put their lock in it if they were working on it. And so until no, we had we had structures there that were generating literally billions of volts of kinetic energy. Well, if you were in those areas, yeah. But even in our little test stand lab, we were at our beam dump. We would pump enough of a beam current in it, 2.5 MeV beam current into that beam dump. That meant the beam dump would actually charge up to 2.5 million volts. You didn't have to get too close before it would reach out and touch you. I don't play. I'm seriously, when it comes to the high voltage, even house current, I'm a complete coward. I do not play that. Papa don't play. I don't do roofs, and I don't do high voltage. Because, I'm dealing with microcontrollers and printed circuit boards, and if I really completely mess up, the most I'm going to do is wipe out a circuit board. I might blow through a couple $1,000, but I'm going to walk away from it without it being any worse for the wear. You start fooling with that high voltage stuff, one mistake, and you don't get a second. No mulligans. Yeah, no, you don't do that. Especially if someone's being held by the voltage, don't grab them to try and pull them off, because then you're just going to join them, and then it'll be two people stuck. You might, because you don't have any clue just how hard that is holding on to them. That's right. If you can't, then say a prayer. I mean, at least pray for their soul as they're leaving this world. It's like cow tipping. It's a great urban myth, but have you ever tried to tip a cow? No, and nobody that's ever been around a cow would. It's 2,000 pounds of animal. It's like arm wrestling a bear. You're going to tackle a cow. They do. Well, is it easier to tip over your truck when it's parked?
Maybe they're like
Look, you get 300-pound refrigerator Perry on the Chicago linebacker. How hard would it be to body tackle him? And he's only 300 pounds. Bobby Boucher. Mama was wrong. No, you wrong, Colonel Sanders. Oh, that is a funny movie. Well, gentlemen, I will see y'all on Monday.